right. Hi, everyone. My name is Chris, and I got Andrea with me, and we like to talk about open source firmware testing with ConTest today. So what I want to talk about, first thing is, of course, the problem statement, right? So what is actually the problem right now with OSF testing? Why do we actually care, or why are we actually talking with you here? What are the goals? What should be the goal of OSF testing, the community, the companies involved, etc. We have a small demo that we can show you. Then we present our solution that we came up with in the last couple of months. And part of that solution is one scenario with the OCP HSMT version 3 Delta Lake. Okay, so the problem. So what is the problem here? Firmware itself runs differently on each and every hardware, right? And that is a major problem when it comes to testing. Firmware behaves differently on different architectures, on different SoCs, on different boards. Whatever components are involved in that whole setup, it actually changes how the firmware runs and the firmware behaves. Most hardware contains quirks sometimes, right, which firmware has to work around, and that changes how many hardware is actually involved. And that means, in total, that firmware testing is hard, because the diversity of all the hardware actually which is out there, and if you have, for example, a common code base which needs to be tested on different parts of the hardware, that makes testing quite hard. Right now, there is no unified approach to this. So there is not like an easy 17-step plan that someone made up yet, who says, okay, if you want to get in contact or got to get in touch with firmware testing, and you like to set up it yourself and you test your firmware on a regular basis, go this road, right? There are these steps that you can take, and then you reach your goal. So that is actually not there. Also, what we noticed that it's quite complex to set up. There are a couple of projects out there which can be set up, but firmware testing often involves like hardware modifications. You have to set up your own whole infrastructure, where to get the code, how to build it, and all that kind of things. So from a technical side, it's quite hard to set up on your own, right? Also, and that's actually the most crucial thing, is there's no central entity right now for firmware testing. So there's not only in one place I can go to get informed about these kind of things, and also where maybe every result or every test that runs somehow runs together. So you always have to collect your information from around the web somewhere and put them together to a bigger picture. I mean, the thing is, the open source firmware ecosystem is quite diverse, which is actually a good thing, right? So there are so many different projects out there, like there's Coreboot, which I do personally work a lot with. There's Tiano Core, EDK2 platforms. There's Slim Bootloader, U-Boot, Or-Boot, whatever there's a lot of different projects, and every of these projects does it somehow differently. So there's no common CI that they use. Coreboot has Garrett system, for example, where Jenkins is actually attached to this, which does the build testing. Or-Boot uses, I guess, GitHub or so. So that is like the part that does the testing there is also quite diverse, and that is also that thing that changes from project to project. Also, what do you have at the most level is actually build testing, right? Because testing on real hardware is hard. What you can do as a minimum barrier, at least, if the code that you write actually builds. You do not know if that code runs successful on hardware, if it crashes, or if it actually enables the feature that you wanted to add, right? You do test that, of course, while development on your hardware or on your development machine. But is that if the feature works on that machine, is it the same for each and every other machine? And that's the problem, right? No testing on real hardware is done. I know that, for example, for the Coreboot project, there's some Lava QA system that gets hooked in after every submit, for example. That only tests on a very little amount of hardware, and that's only some basic testing. But that's like the minimum that I have. I'm quite sure that other companies also do some testing in their own company, but there's no unified place where these are somehow gathered together. So imagine this, right? You have a project. This project has 100+ contributors. Not sure how many code it has, but it's quite a lot. And I just checked the commits that came in the last 24 hours, and it was roughly 75 commits that got merged. It was a quite busy day, so normally it's around something between 10 and 50 or so, but 75 can also happen from time to time. Each of these commits can actually introduce a regression. And so no one of us is perfect. And I do write code that I can actually introduce errors, right? Because I do test it on my machine on a very special hardware and on a very narrow piece of the whole picture. And it works on that part. But maybe I didn't test all the corner cases and not all the hardware that is actually out there. So that means it can introduce regressions, it can introduce errors. And I don't know who ever tried to find a bug in these kind of projects. This takes time, and this takes actually a lot of time. Bisecting, for example, for a project takes so much time. You always have to rebuild the binary, you have to test it over and over again. Sometimes you can only reproduce it under certain circumstances. And to get really to that commit, what actually broke the tree in the end, takes a lot of time and a lot of money. And I guess both is a thing that a firmware developer normally has not, right? So we do not have time, we do not have a lot of money, so we want to keep that very, very low. So what would be here the goals, ideally, right? More OSF testing, obviously. The more we test, the better it will be. So if we can hook up more hardware into an infrastructure or generally to the OSF testing, then that would be great. Also, testing should be more accessible. Right now, as I said, setting up that system on your own, it's quite a struggle, right? You have to dig into all these kind of things. You have to do hardware modifications and blah, 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 the whole type of thing. And that is quite a struggle. And you want to have that more accessible. And also the results that you gather on your hardware should be somehow shared across the community, and it should be accessible around across the whole community, so that everyone can access your results and maybe integrate that into their own CI or so that we benefit from each other somehow. How can we do that? So that's actually the big question here. Okay, we actually came up with two major things which need to be in place. So we need to have a decentralized testing infrastructure. So that means everyone around the globe somehow should be able to test, to set up their own infrastructure, right? Just a small portion of the whole picture, but still a small portion. You do not want to have like centralized places where all the hardware gets tested, where you have to, I don't know, send your board or drive to or fly to, whatever. So everyone can actually submit boards to that QA. Yeah? And that would also mean that the boards would be kept maintained, right? Even though if people maybe do not take care of that part of the code anymore, if the board is still in there, it's still maintained there. And that is actually a very, very crucial thing, because if errors come up on these on that board, people tend to fix them, right? It's open source, you can do it. You need a centralized reporting infrastructure somehow. So as I said, results should be usable across the community. So that means there should be one place somewhere where we do gather all that reports, so that these reports are actually accessible for everyone. So everyone can actually consume these results and integrate them somehow in their own project or integrate them in the own firmware projects. Of course, results should be shared with everyone, right? So that's obvious if you have a central reporting infrastructure here. Okay, what are the pros and what are the cons of these kind of things? The con here clearly is we need to do work, okay? We need to agree on a common test interface or a specification that we say, okay, if you post to that central testing infrastructure, it has to be in this shape. I mean, that's just natural. We have to agree on a common language that we need to talk so that we can actually work together. Integration work is another thing that will produce a little bit of overhead here. So that means integrating the fetching of that results into your own CI or into your own system, that will produce some overhead, right? And of course, on short term, there will be more fragmentation. The solution that we show up and the use case that we came along with use ConTest as a framework. That introduces another testing framework somehow. So that is actually more fragmentation on the market in the short term then. But the pros actually overweight here, okay? So we got better test coverage, which is obviously what we all want. We do measure the impact of features that get added to the tree, okay? And also not only on your platform or on that specific SOC or architecture or board, but on all of these kind of things. We do catch regressions. So that is a crucial thing. If you, as we do it here, actually work with that on a business level, you don't want to have like a broken master tree, right? We keep unmaintained boards in the tree, which is, I guess, very useful for the community. You always see, okay, which boards are actually hooked up in the CI right now, and what is the status of these boards, and are they maintained? Are they working? So is the master tree right now working of these kind of boards? Nice, I can grab one of those and flash my OSF on it, right? And the biggest pros is here that we are combining multiple efforts. Because we're splitting up in like a decentralized testing infrastructure, but still a centralized place where you actually gather the results. You can do whatever you want in your decentralized testing infrastructure. Run whatever system you want, I don't care. As long as you speak the same language when it comes to the centralized place, we're all fine, right? Okay, so we have a short demo now on how we integrate things. You will actually see how it all works a little bit together. So we will not deep dive into it, what is actually happening there, but more about how you use it and how you trigger off a job. The technical deep dive will be done by Andrea later on, so that you get a better grip on what is going on there. We got two things here, right? On the one side, we got the ConTest server who actually receives the job and then works that one off. It's also the build server in our case, so that one is also building CoBoot, for example, and it is also flashing the device that we need to test here, and also testing the device later on. The second thing that we have is the ConTest CLI, which is triggering off the job, more or less. So I will just start the job from the CLI, and then we see how it will get processed on the ConTest server. So you just take the ConTest CLI, specify the ConTest server that you want to post to, and start the job. The job definition actually, so what jobs should be run and what steps should be made, is in the Delta Lake JSON file. Now, so we're running a job for the Delta Lake EBT machine here. So if we trigger that one off, so that looks good. On the other side, you see that it received the job here. So that's like a full description of the job. We will have a link to an example within the presentation later on. And now you see that it actually started working, right? So it starts cloning the job and works with it. On that side, it now actually waits until the job to finish. When the job is finished, you can actually fetch a result of the job. The result is like a full result on what has happened and if there were any errors on the way or whatsoever, like also with reporting. There's like a very short section on the top of the report, which gives you an overview what was successful and what was not. Let me just scroll there. So we will see, okay, the building boot of the CoBoot actually passes and was 100% successful. And also the cleanup, of course, was successful. We do also have an example of that linked later on the presentation so that you can actually check it out online, how a full result actually looks like and what detail level it actually gives you. That actually comes along with the request. Okay, so what are the results here? So what came we up in the last months, right? So we made up that infrastructure here, which basically looks like this. We get different test setups on the left side, which in our case is ConTest. but it could be any test setup that you want actually. That test setup actually does the job, proceeds the job, does the testing, and that one pushes the results to the S3 bucket. The S3 bucket is our centralized place where we actually store the results right now. That S3 bucket can actually then be consumed by other systems, right? For example, the Cobalt board status page could consume that S3 bucket and that results, JSON file results, which are actually in there, and make up that board status page. Also, TianoCore or other OSF project could consume this results and integrate that into their own CLI. We have an internal CLI where we actually consume these kind of results, and also your companies or your personal CLI that you have set up can actually work with the results that we're pushing to. The reality is that is what we did. We have on the left side, we have the Delta Lake setup. So that is the ConTest setup that I just showed you and that we dig into a little bit deeper, that we dig into a little bit later on. This is what we worked on the test setup. Now we're pushing everything into an S3 bucket, and that gets consumed by an internal CI system right now. We are planning on to hook that up with the Cobalt Garrett system. Okay, so what is ongoing here? The ongoing thing is we are gathering results in a centralized place, which are actually accessible for everyone, right? We have set up the OTP Yosemite version 3 data lake testing, and that tests actually the current Cobalt master branch against that Delta Lake system. Our vision is that we can work out a draft for test result specification so that we have, as I already said, initially a common specification or a common language that we all speak so that other test setups can actually contribute to that centralized system. Also, we want to attach other OSF project, right? So the first idea that comes to my head is the Cobalt board status. I mean, that looks quite messy, no offense here. We could actually clean that up a little bit. And if we hook in more boards, we could integrate these information that we get from the test system and integrate that into the board status page, right? But in general, it's more hardware, more projects, more testing.
Thank you, Chris. And hi, everyone. My name is Andrea. I work at Facebook as a production engineer. And in the last couple of years, I've been focusing on open source firmware. I'm going to discuss our solution and basically describe what were the things that make up what we used for this demo. So from the hardware side, we used two different machines. One is one Open Compute Yosemite v3 node with Delta Lake architecture, and one Raspberry Pi. Those two machines I will show in the next slides how these are hooked up. On the software side, instead, we use ConTest, which is an open source general purpose system testing framework. It was developed at Facebook and made open source on GitHub. You can see the links in the slide. And it's currently used internally to test for various purposes, including testing of the firmware, but it can do much more than just that. We are using it for daily testing of our own open source firmware, for example, the ones that are running on Facebook's Minipack platform that was discussed in the previous Open Compute Summits. So let's see some of the properties of ConTest. Obviously, we wanted ConTest to be open source because we are working with open source firmware and we want to have a fully open ecosystem as well. And it's a general purpose system testing framework. It's not just for firmware. As I mentioned, it can do much more than just that. And it can actually control anything. It can actually test anything that you can control automatically. It's a modular system as well. Basically, you can specialize it if the existing components do not fit your purpose. You can always specialize it with additional components that work with your infrastructure and make them fit with a broader system. ConTest is also a validating system. We try to minimize as much as possible runtime errors because we don't want, for example, a 6-hour test or even longer, 24 hours test to break late and waste a lot of our time when we know that something could have been caught earlier. For example, a plugin bug, a plugin misbehavior, a configuration misbehavior, etc. permissions, lack of permissions, and so on. So this is validating as much as possible early at compile time or at job submission time, and only a few things can actually break it at runtime. It is configuration-based. What this means is that you don't need to be a software developer to understand how ConTest works and how to operate it. But you just need to describe what you want to run as text files, like JSON or YAML, and the framework will do the job for you, will interpret it and do the job for you. ConTest can also run tests either on device or orchestrated. On device, it means that, like many other systems, similar systems, you can run directly on the device under test. But orchestrated is also useful because you cannot always access the machine because maybe it doesn't have way of letting you remote access like SSH or console. But maybe sometimes you just have to do something on the machine through some other system, like, for example, a VMC. Next, I'm going to show an overview of how this works. In this diagram, you can see on the left-hand side, there is one of the two components, which is the Raspberry Pi that is acting as a controller and as a client. On the right-hand side, you can see there is the ConTest server that is running on the Yosemite v3. And so the workflow is like this. The Raspberry Pi submits the job. You can either submit it manually by calling ConTest CLI from the Raspberry Pi, or if you've set up a continuous integration, you can let it run continuously, either on diffs whenever there is a new commit on Gerrit or every few hours. That really depends on your use case. Then the job is submitted to ConTest as a JSON document with the description of what you want to run. The first thing that ConTest does after validating the request is to check whether it can acquire the machines that you want to test on. For example, in this case, we are testing on the slots 2, 3, and 4 of the Yosemite v3 Delta Lake. If it can acquire all the machines, it will also lock all of them. So it will also avoid that other constant ConTest instances will use the same targets at the same time. So you avoid race conditions in this case. Once all the targets are acquired, the test steps are executed in sequence independently for every device under test. In this case, the 3 slots. In the example, we are building, we are fetching and building the latest core boot, and we can also flash it, reboot it, and check from the console that everything booted properly. This is all stuff that you can specify in your steps. The tests are run independently. ConTest will orchestrate all of them independently, and when everything is done, the results will be reported back to the client, which is running on the Raspberry Pi, which will eventually have a JSON file which contains all the information about the job and about its results. And these results will be pushed to an S3 bucket, as Christian has mentioned earlier. Next, I want to show you an example of a job request. We said it's JSON. It could also be YAML. That is a more compact format. In this snippet, I'm showing only part of what you can specify in the request. Specifically, one of the steps, the syntax of one of the steps that you can run. The target acquisition is something that I'm not showing here, but you can click on the URL. You can open the URL on the slide and see the full description itself. The test step that is shown is actually showing several fields like label, name, parameters, executable, etc. What this means is pretty self-explanatory. The label explains what this step is doing. The name is the name of the plugin that is executing your job, your step. And the executable and the arguments are passed to the plugin, which will know how to interpret them. In this case, we are using the command plugin, which executes commands locally to the ConTest server. And you can easily figure out that what this is doing is running git clone with a specific URL in a specific directory. You may have noticed that there are square brackets and some get GitHub repo string in there. That means that we are using templating. Templating is useful when you don't know beforehand what some of the content of your request should look like. In this case, for example, we want to dynamically generate the name of the GitHub repository and the name of the output directory. So in practice, this is telling you that we are running an internal function called get GitHub repo, which receives as an argument the ID of the machine that is being tested. And the same thing happens for the temporary directory /tmp/coreboot - the name of the machine that is being tested. Then next, I want to show you an example of a job report. Again, you can see the content of this job report at the specified URL. The job report contains a lot of information of which we are only showing a part. The job report that we are showing contains, as you can see, the server that has been running the job, so you can identify where this has been run. It will show you whether the job was successful or not, when it started, when it ended, what were the steps that it has run, and whether the reports were successful or not. I said reports, plural, because there are multiple reports that you can actually request. You may be interested in the total success rate of your test, but you may also be interested in the performances of your test. So in one case, for example, your jobs may be successful in terms of how many machines completed and booted correctly, but you may notice that the performance regression testing is showing you that these machines are taking much longer than we want. So this means that you can actually run multiple types of reports. There is no single source of truth at the end of the job. At this point, I'm going to hand off the mic again to Chris, who's going to talk about the scenario with the OCP Delta Lake.
Yeah, thanks, Andrea. Okay, so the OCP Delta Lake, or the OCP Yosemite version 3 Delta Lake, is the one that we used for our testing. It's a multi-node server platform, as Andrea already said. It has four slats per Yosemite version 3. So as you can see on the right-hand side on the picture, there go 4 slats into that server system, into that multi-node. Each of that has one socket system, which is a Cooper Lake Xeon SP CPU on it, 52 threads, so that's something that you can actually work with. It has around 96 gigabyte of RAM, and they all do share the same 200 gigabyte NIC. So if you want to see one of these systems, I got them one lying next to me. That's basically how it looks like in the close-up here. All right, so we thought about what we want to do here, and we came up with that idea that we want to test. Okay, let's test the coreboot master against the upstream. So the upstream master. So what is actually the tip of the coreboot tree right now? We do take a fixed uroot and linux-boot commit as a payload that can later then boot into our operating system. We do that on a fixed interval. So we do per diff testing. That means that we do not test every commit submitted to the coreboot system directly, but we rather test it on a fixed interval, like every hour, every 2 hours, every 4 hours, and then only test the diff that actually has happened here. We do basic build and boot testing, so that is like the barrier that we have to jump over. Coreboot has to boot correctly, and it has built correctly and has to boot into the operating system to be successful. Afterwards, we push these results, as Andrea already mentioned and showed, as a JSON file to the 3 bucket. The cool thing, or the nice thing, is here that we can actually use the BMC to flash the device under test, right? So that means that there's no hardware modification needed for that, so there's no soldering whatsoever involved here. This is a more top-level overview about ConTest. That I took from one of Andrea's talk, and I just want to show you what types we touched here. And we basically only touched really the test steps, right? All the other system, like the job manager, the runner, the API, and so on, that comes for free with ConTest. We only specified what test steps should be run here. How did we do it? So we specified 3 tests. Each test actually can have multiple test steps in it. And if one of the test steps within a test fails, actually the other one will not be executed anymore. So what we did is we divided that into three test steps, or into 3 tests. The first step is like the preparation of the target. We need to pass around some SSH keys, need to do some cleanup maybe from the prior job or so. so that we have to prepare the environment somehow. That could also involve, for example, provisioning the device under test with a proper Linux system, right? So that is something that always needs to run. After that, our real test actually starts. So we do fetch the core boot master tip, build everything together, burn it on the device using the BMC, boot the device and boot it into the operating system, and while booting, gather all the logs that are actually produced on the serial console of the device and look for certain occurrences of strings here. Yeah. So what we want to do in the end is we want to have no errors in the boot log from the kernel, and we also want to reach the login shell. Once that is done, we do a cleanup. So that means cleaning up all the binaries that we placed on the BMC and so on, cleaning up our temporary directories and so on and so on. So the ConTest is ready again for the next iteration here. What we like from you, or what we want to anticipate here, get involved if you want to, right? So one of the biggest hurdles here, I guess, is drafting a test interface specification. So we need to agree on a common language here that everyone wants to talk. And that is something where we need your help. I imagine that you have a couple of test systems already integrated somewhere and already in place. We like to know, okay, what do you have? How do they talk? How can we find a common language? What makes actually sense to put in a test result, which can then later gets placed in a centralized place? Hook up your hardware, obviously, right? As I said at the beginning, we do need more hardware setup. We do need more OSF testing. So that can only work if more people actually put in their hardware. We can help you with this. So you can find us on Slack in the ConTest channel. So on the open source firmware Slack, you need to get an invite on slack.osfw.dev and join the ConTest channel. So there you can find me, and there you can also find Andrea. Just ask for help. We are there, and then we can help you set everything up. With this, I'd like to thank you for listening, and I hope you enjoy the OSFC.